In this video, we're going to describe and define the constants Kb and pKb. So when you have a weak base and it's dissolved in water, the base will accept a proton or an H plus ion from the water molecule. In this example, we can see the ammonia molecule, which is our weak base, is dissolved in water, and the ammonia will accept a proton from the water. So the water is acting as an acid. Ammonia is our weak base. We form a protonated form of ammonia, so we form the ammonium ion, and the water will lose a proton to form hydroxide. So we form a conjugate acid, ammonium, and a conjugate base, in this case hydroxide. So this process of protonation and deprotonation will eventually reach equilibrium, where the rate of the forward and reverse reactions or processes will become equal, and the concentrations of reactants and products will remain constant. So anytime we have a process or reaction that is at equilibrium, it can be described mathematically or numerically by an equilibrium constant. In this case, we call the equilibrium constant Kb, the B representing a base, since we have a base being dissolved in water. And our equilibrium constant, our Kb value, like anything, any equilibrium constant, is temperature dependent. So as long as we keep the temperature constant, our Kb value will be a constant. So just refresh your memory on how to write an equilibrium constant expression. It's always going to be the concentration of our products divided by the concentration of our reactants raised to some power, and that power is dependent on the stoichiometry of the reaction. We do not include pure solids or pure liquids in any equilibrium expression because their concentrations are constant. So back to our example of ammonia dissolved in water. If you would, pause the video briefly and see if you can write an equilibrium Kb expression for this process. Okay. So our Kb is going to be the concentration of our reactants. It doesn't matter which order you write them, raised to the first power, divided by the concentration of ammonia to the first power. We would not include water in our equilibrium expression because it's a pure liquid. So Kb is important because it's a constant. It gives us a measure of how readily our base will accept a proton. In other words, it gives us a measure of how strong a base is. The larger the Kb value, the stronger the base is. So if ammonia had a large Kb value, that means the concentration of our products at equilibrium would be very high relative to the concentration of reactants. In other words, the reaction would proceed very far to the right before equilibrium was reached. If the Kb value was relatively small, the reverse would be true. In other words, the reaction or process would not proceed very far at all before equilibrium is reached. So if Kb was very small, we would have a high concentration of ammonia, and very little of our products would be formed when equilibrium is reached, so that it would be a very weak base, and we would have very little protonation of our base. Now strong bases, again, Kb is generally reserved to describe weak bases. Strong bases are generally ionic compounds that contain the hydroxide ion. For example, sodium hydroxide, calcium hydroxide. These are generally ionic compounds that are soluble, and they produce the hydroxide ion. So for strong bases, all of the hydroxide ions are protonated. In other words, the reaction occurs 100%. So there is really no equilibrium that's reached. The Kb values for strong bases, like strong acids, are generally too large to calculate. So Kb values are generally only associated with weak bases. Now there are some other strong bases other than ionic compounds with hydroxide ions. You can see hydride and amide. These are very strong bases, so their Kb values are too large. But you can see some of these other weak bases. Here's just a few examples. The phosphate ion, ammonia is in here. So something like the phosphate ion, PO43-, would accept a proton from water, and you can see that the Kb value is much larger than that of, say, aniline. So in other words, this process occurs much more readily, the protonation of phosphate, than the protonation of, say, the aniline molecule. And we can see that based on their Kb values. So be sure you appreciate what the numerical value, what information we can get from the numerical value of Kb. So Kb constants can also be expressed in terms of pKb, where pKb is simply the negative log of Kb. Kb and pKb are inversely related. And what we mean there is that if the base has a large Kb, the pKb would be relatively small. And if a given base had a small Kb value, then that same base would have a relatively large pKb. So be sure you convince yourself of that. Plug in some numbers into this equation and play around with it to convince yourself that this relationship is true. So therefore, what that tells us is that weak bases that are relatively strong have large Kb values. Remember, a relatively strong weak base has a large Kb value and a small pKb, and vice versa. Weak bases that are relatively weak have small Kb values and large pKb values. So let's take a look at a problem. Read over this problem, pause the video, and see if you can solve for the Kb value for this weak base. Okay. So first, we're asked to write a Kb expression. So let's write our equation showing methylamine in water. Methylamine is a weak base, we're told that, so it will accept a proton. And here you can see we've gone from NH2 to NH3 plus. Remember your charges. And the water will lose a proton or donate a proton over here. And so we would form hydroxide. Now we should be able to write a Kb expression where we have our products, concentration of the products, divided by the concentration of my reactant without water included. So we're given that the pKb is 3.359. What would be the Kb value? So we have to rearrange this in order to solve for Kb. So Kb is equal to 10 to the negative pKb. So what I would do there is take my pKb and 10 to the negative 3.359, and that should yield 4.38 times 10 to the minus 4 for the Kb value. And Kb as well as pKb, there are no units associated with that value. So be sure you understand the concept of Kb, and you can convert that into pKb or vice versa if needed.